What? Welcome to Logs Vlog, Day 2, a thermal chem unit. Whoop whoop, here we go. We talked about how delta H is called enthalpy. It's the change in energy from the reactants to the products. In chem, we like to be specific. Supposedly it makes things easier for us. Sometimes you'll see us write little letters after the delta H symbol, the change in energy symbol, so we know what type of reaction we're talking about. So, well, delta HCOMB. We're creative here. That's the change in energy in a combustion reaction. Delta H VAP is the change in energy for vaporization. So if you're boiling something, here's the change in energy for it. Delta H condensation. This one makes total sense. The next one, delta H fusion, not nuclear fusion. That's the fancy word for melting. All right. Delta H solid is delta H for solidification, and then later on we'll talk more about delta HF is for what we call a formation reaction, which is the exact same thing as a synthesis reaction. One thing I want to point out from last unit when we talked about phase changes, you know how if you boil something, you have to add energy to it? Endo or exo? Endo, because you have to add energy to it. For something to condense, it has to lose energy. The molecules need to slow down so the intermolecular forces can kind of recombine together. This is the same kind of change in energy, but one is positive and one is negative. Since we're going through the same phase change, it's like we're approaching that phase change graph from opposite sides. So like delta H VAP will always be positive. Delta HCOND will always be negative. Combustion reactions, you can guess, they're all exothermic. They're always going to give energy off. But these values for the vaporization and the condensation will be the exact same amount of energy. And the only difference is that one's endo, one's exo. That idea is the exact same for fusion and solidification. Which one is going to be endothermic? Melting. Picture, in order for an ice cube to melt, it has to absorb energy from the surroundings. So this guy's going to be a change in energy that's positive. Freezing, we have to take energy away. It's going to be negative. But I will tell you, out of all these, combustion is going to have the biggest change in energy because now not only are we breaking intermolecular forces, but we're also breaking the actual bonds, the ionic and covalent bonds that hold the atoms together. So, and then if we don't really know what type of reaction we're talking about, we just write RXN, Rickson reaction. So if we matched, look at, see how that's a combustion reaction? You would have, that would be delta HCONB. This guy, we're going from a solid to a liquid, that represents a fusion reaction, delta H fusion. Oh, liquid to gas, that's delta H VAP. We are taking two elements and we are making one compound. Synthesis reaction, we would symbolize that change in energy with a little F after it. Liquid to a solid, what is that? I'm trying to think. Delta H solidification. And then this guy is just your straight up normal double replacement reaction. We don't have a fancy symbol for it, so we would just write delta H for this reaction. So just FYI, if you end up, Googling or reading any more about changes in energy and you see those symbols, that's all that's referring to. But what I did not talk about yesterday, which I'm sure you're going to be really thrilled about, is how we can do stoichiometry with it. I forgot this slide was here, so let's talk about it. I'm gonna go back. Maybe we'll hit it here. I want us to compare two numbers. I want us to compare the vaporization and the melting. So they're both phase changes, and they're both endothermic. But take a second and think about which one is going to require more energy, have a greater change. Turning something to a gas or turning something to a liquid. turning something to a gas, that vaporization, is going to have a greater change in energy because you're completely breaking the intermolecular forces that are there. Where if you're melting something from a solid to a liquid, those intermolecular forces still exist. So the heat of fusion, so melting, is always less than the heat of vaporization. So all we're doing is kind of changing those forces, but here in going from a liquid to a gas, we're completely breaking the intermolecular forces. So here's another thought. Water has a higher amount of energy, change in energy to melt it, than ethanol does. So which one has stronger intermolecular forces? Dora. The water does, because it requires more energy than it does for the ethanol. That means that those things are being held together, those water molecules are being held together a lot harder and tighter than ethanol is. So that's why its change in energy in order to get it to melt is greater. So I'm going to write water here. So there's kind of some chemexy questions we can ask. But another fun thing, which is what I wanted just to show you today, is how we can actually do stoichiometry with energy. And you've done this before. So back in Unit 4, when we did stoichiometry, I had thrown a couple problems in like our second homework that unit that had energy in the problem. But let's try this. I'll walk through a couple with you so you're kind of good to go. Energy can be written in the balanced equation. And that's kind of our goal for the end of this unit, is to be able to write a balanced equation and include the change in energy in it, balanced. So just to do some stoich with this, first thing we need is a recipe. And we are taking propane, which is C3H8, and we are going to combust it, which means we're reacting it with oxygen gas. I'm going to be lazy and not write the sticks of matter. My handwriting's not neat enough to handle it. Notice how the change in energy for this combustion reaction, do you see how it's negative? That just means it's exothermic. It's being produced. So I can include energy in the reaction. And because it's exothermic, I'm going to throw it on the product side. It's being produced. And for every 1 mole, which I probably should balance it. I think we got this, and that. Now we're balanced. So for every 1 mole of propane that's over here, it gives off 2,219 kilojoules. Here's my balanced equation. And now we just approach the problem as any other stoichiometry problem. I've got 20 grams of oxygen gas. I think I just added a sig fig in there. Sig figs. There's my dot of O2. I'm putting that over 1. We always need to take grams, and in order to use our new molar ratio, we have to take grams and turn it into moles. So I'm going to write 1 mole of O2, and I would find that number on the periodic table. So 2 O's added together is 32.00. And then I want to figure out how much heat, that's the kilojoules, how much energy is being given off. So because I have moles of O2 up top here, I'm going to write moles of O2 on the bottom. And because I have my ratio of moles of O2 to energy, I can include energy in the molar ratio. So for every 5 moles of O2, I'm going to produce 2,219 kilojoules. So if I cancel units out, grams go away, moles of O2 go away. Do you see how the only unit that I'm left with is energy or heat? I'm going to have my answer. And with 2 sig figs, I think you get 280 kilojoules. And you can just stop there. Stoich with energy. Okay, let's do one more. I'm going to rewrite our balanced equation. We had propane, just so we've got it again. Oh my gosh. There we go. C3H8 plus O2. I'm going to write 5O2 makes 4CO2. Not 4CO2, 3CO2, and 4H2O. And I'm including the energy, 2,219 kilojoules, just like I did before. Oh, let me move my picks in the way. Okay, this problem, we always take the number we're starting with and we put it over 1. I'm going to write 200 kilojoules. over 1. The unit of kilojoules goes on the bottom. And this is where, again, I'm going from kilojoules to CO2. I can just straight up use that number that's in the balanced equation as part of the molar ratio. So I'm going to write 2,219, and I'm going to write that's when 3 moles of CO2 are produced. I didn't specify what we were solving for, so I'm going to leave it at moles. I'm going to write 0.270 moles of CO2, but if I had asked for grams, you would just do the next step and take the moles and turn it into grams. So what's the only way to get good at this? Practice. I've posted the homework we would have had in class on day 1. It's there. I will post an answer key as well. And then this yesterday and today is essentially what our next quiz is on. Peace out.